Hey guys, so we're going to be moving on to the second volume of Apostles Calculus 2. Um, I have a quote here divided, yeah, divided by. So it's going to be divided into three sections. This book is analysis in the linear and the nonlinear sense, as well as special topics which we'll cover like set functions and all of these things, which kind of combine elements of linear and nonlinear analysis. Um, Again, this is a calculus book, so it's the sequel to the first volume that kind of develops just the idea of um, integrals and you know derivatives and how to define them in a way that's natural. Um, so yeah, that's pretty much it. I mean, everything that's going forward with Apostle in his volume two, I guess the main goal is just to make sure that you convey this pure mathematical type of rigor. Um, with the spirit of modern mathematics, and you need to develop the skill of formalization. So formalization gets really emphasized in the second volume on how to, formulate such, and explore a different things. So of course he goes into linear spaces, linear transformations, determinants, um, eigenvalues, eigenvectors, eigenvalues operating on Euclidean spaces, linear differential equations, systems, and so that would be linear analysis as a subject. Now, this would actually be interesting to tie in with linear algebra. She loves linear algebra. It would be an interesting thing to try to, I guess, develop some kind of study plan that looks at the intersection, that gets motivated in here from a calculus textbook, um, and from this kind of semi calculus to like rigorous, um, formulation of uh, axiomatic linear slash like affine spaces in general. So it does a really good job of doing this. Talks about uniqueness. Uniqueness is talked a little bit more in the differential equations. It's expanded upon as well. So it's just nice progression here for the linear analysis section. The nonlinear analysis section starts to define um, differentials upon scalar and vector fields. So you can have different types of Euclidean spaces, open balls. So you get some topology as well, um, and some of the language that's used in topology. It's and the level of thinking behind it, the first principles, um, like fundamental, like irreducible um, things are emphasized in this book for nonlinear analysis as a complete subject as a whole. And you can kind of think of this as like a draft for then being able to apply it to differential calculus, which later gives you the way to think about cohomology, de Rham theory. You'll get line integrals, multiple integrals, define iterative integrals or integrals of multiple functions over some domain. Then you'll get surface integrals, and so those are the things that you will be able to do after nonlinear analysis. And uh, yeah. And then lastly, how the book decides to end is to end with set functions and elementary probability. So what's cool about this is you will get some notions, if you will, from measure theory, and taking the nonlinear and linear analysis to then start defining combinatorics in a nice way. Hold on, sorry, I had a terminal pop up. Um, Combinatorics, distribution functions and generals for defining probability in general. Uh, the introduction to numerical analysis as well. This is just another kind of nice addition to being able to actually physically compute things. So that's what these texts are. A lot of reading between in apostles. calculus 1 and 2 series, but it's essential. So, and it's motivated in a way that's uh, very contained to allow you to have the background that's necessary to get into something like linear algebra by Shilov or etc. So it helps you fill in a lot of the gaps for um, conceptually what's happening. So let's start with linear analysis. Um, Really, what this does is it just moves to inner products. There's a kind of an axiomatic linear. So of course it lays out the axioms for a linear space, just like any other linear algebra book would. Um, but you get the axiomatic definitions. But really, I think the construction of orthogonal sets is introduced right out the get-go in chapter 1. The Gram-Schmidt orthogonalization process is right here. And this is the theorem basically how to approximate elements in Euclidean space. So, you're automatically getting the tools that are necessary for preparing yourself for things like Fourier analysis, approximation theory, infinite dimensional Hilbert spaces. All of that depends on your Gram-Schmidt process. So, this you get a nice introduction to this geometric type of projection analytically right out in the first chapter. So you're basically primed for advanced functional approximation already. All right, and then let's just move on. I'm gonna try to make this pretty quick. Transformations, because all of this gets covered in the other linear algebra thing that I covered. So I don't really want to have like too much overlapping content because these are like really basic things. Yeah, you'll have the concept of null space and range. The text explores nullity of rank and transformations. So we'll go through how the operator, like you'll define operators in themselves, linear equations, projections on subspaces, and then nullity. And you can think I would say isomorphisms between linear and transformations of matrices as well are established. So this kind of reflecting on this, right? If I was to take calculus again with this book, like I would think about this fundamentally from like a systems of linear equations for the computation of like matrix inverses. Like all of these things are super. This is heavy machinery for like what people are actively doing in the field. So you want to emphasize this isomorphism between linear transformation and matrices, simply because it'll introduce you to the idea of like category theory, structural equivalence, and abstract algebra. So you're getting that pure mathematical, you're getting a logical progression into pure mathematics. That's like kind of just each concept builds upon the next one in such a way that's you know we talked about distributive laws for matrix multiplication. So yeah, it builds a mental image that makes a lot of sense, and it's a way to just get the quick and dirty types of computational things out of the way. Determinants. So determinants then is now introduced. It's different from Shilov's, where determinants themselves are motivated in such a way that would give you like the multilinear algebra perspective on it. From a purely like parity type of combinatorial approach. But determinants here, you're instead of relying on the permutation definition of determinants immediately, for like you read Shilov, apostol, he's going to give you motivation for the choice of axioms. So of I think determinant function. That's what he uses. Yeah, choice of axioms for determinant function. So he's going to define the first of all, he defines the determinant as this unique alternating multilinear form on the rows of a matrix, and then it'll give you this nice, it actually does give you the tensor algebraic perspective, set of axioms for a determinant function. So yeah, he goes through um, and kind of justifies this and the computation of the determinant. Um, but it's like a nice coordinate free, I would say, a tensor algebraic perspective. Um, and so the uniqueness as well of the uniqueness theorem of the determinant, I think, is covered in here as well. Yeah, here, perfect. Yeah, the uniqueness theorem, it should be. And you'll get product formulas and expansion formulas, minors and cofactors that naturally follow from everything. So you get, I mean, you're getting this pure axiomatic um, treatment that will give you the idea necessary for um, computing differential forms on exterior algebras, on manifolds, alternating forms. Really, this is the building block of integration itself. So, in the next, we can continue on with eigenvalues, eigenvalues and eigenvectors. I'm not going to get too into this. I think I would actually say right here with determinants is a good place to stop and then read She Loves Linear Algebra until you get to the spectral theory type eigenvalues chapters, and then come back here. That makes a lot more sense to me. And in fact, I might go ahead and reread that in such a way and see like if that makes sense to me. But yeah, that would make a lot of sense to try to read up to here and then open up Shelov's linear algebra book for a little bit, investigate everything up to eigenvalues, and then come back over here and see if you can get something out of it. I mean, there's different ways to approach it. There's not like one single way, but yeah, that's kind of you gotta see the patterns and recognize the patterns for yourself and try to put them all together. So, anyways, um, linear independence. So really, when you get the linear independence of eigenvectors, assuming that you've had some Shilov already, you can just have the foundation of spectral theory from this. And I think he kind of warning the converse. What's theorem 4.2? Theorem 4.2. Oh, okay, okay, okay. Converse does not hold. What does that mean? Understanding. So, okay, that's right, because they represent the invariant directions of the operator. Yeah. Okay. 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 So that's what linear algebra, or that's what the wait. I'm gonna have to think about that a little bit. The warnings. See, like you'll notice different things. Like why does the converse does not hold independent? Distinct. Okay. Okay. They don't have to be distinct. So sorry, I missed this the first time through. I'm writing it down. Theorem. Okay. Anyways, moving on. Yeah. So this is. I mean, this is important for quantum mechanics, study of dynamical systems, everything within here. Now, eigenvalues of operators acting on Euclidean space, and I can't spell. There we go. Eigenvalues of operators acting on Euclidean space. Not too much to say about this that adds anything to Shilov. Hermitian, skew Hermitian transformations get talked about in a calculus textbook. um, existence of an orthonormal set for eigenvectors for Hermitian, skew Hermitian operators acting on finite dimensional spaces. Yeah. Diagonalization of a Hermitian matrix. Quadratic forms, diagonal forms. All of this we talked about in Shilov. So, but it is kind of cool to see that in here. Yeah, these theorems are the mathematical backbone, pretty much, of quantum mechanics. You can think about that, where any physical observable, right? You can model that as a Hamiltonian operator. So this is important then to motivate the probability, or the I guess the statistical multivariate probability that comes later in this book. So yeah, I think we can move on. Linear differential equations. Yeah. Linear differential equations. Now, okay, so apostol is going to treat this differently. Um, so you take the differential equations from the previous volume, right? I think we covered a little bit of uniqueness, and it was just kind of like an introductory type of exercise. Now, this actually is going to give you some maturity on how to think about differential equations, um, because of the constant coefficient operators being formalized. You can think of the linear differential operator itself, as this, or we can get it into an operator type of language. So let's see. Operator notation. Yeah, here we go. So general. Yep. All functions where first derivatives are continuous on J. So let P sub 1, P sub NB functions, and the operator L from C and J to Cj be equivalent to this. All right. And so this is the kth derivative operator, and you or the yeah. This is the kth derivative operator, and the operator L itself is acting on a function. Okay, that's how I think about it. And you can you can use the Wronskian matrix to prove the non-singularity of independent solutions. You've probably seen that in the differential equations class, or you probably will see that if you take one. But the study of Legendre equations as well. He studies Legendre equations here, yeah, which is kind of insane for a introductory chapter. Well, it's not introductory calculus; it's the volume 2. But yeah, he talks about the Legendre equation itself, and how to, uh, and other second order differential equations that are pretty interesting, um, with these nice analytic coefficients to give you special functions, these special types of functions in mathematical physics and Sturm-Liouville theory. So that's how we get different types of polynomials, different types of exotic representations, functions, um, by upgrading ourselves to the language of using linear differential equations as operators. Rodriguez formula, it's all covered in apostol. It's all there. What isn't an apostol? That's the real question. Systems of linear differential equations, or systems of differential equations. Okay. All right. Now, how we can think about this is we have to move out of with the systems themselves. You can model them with matrix calculus pretty much. So you have the rigorous proof of existence and uniqueness for ordinary differential equations, from the ODEs, but now we can use, I think it was we shall use, said that shit. Yeah. We shall use, where is it? We shall use the method of successive approximations. What does that mean? It's an iterative method which also has application in many other problems. So his methodology, you basically are casting it in the language of something called contraction operators. Yeah. So I would recommend going to the introduction to tensors in She Loves Linear Algebra text, um, and then up to there, and then going to systems of differential equations. Reason why you might want to do that is because you can cast uh, you can cast it in the language of contraction operators and like what particularly contractions mean themselves in terms of differential in the context of differential equations. You'll get a contraction mapping principle that is precisely related to the Banach fixed point. It's not. Let's go Banach. Doesn't want to show up. But the Banach's fixed point theorem uh, allows you to think about the contraction mapping. So, oh yeah, here it is. Perfect. It's before you call it the Banach fixed point theorem. But basically, it says if you have a contraction operator, there exists there exists one and only function phi in C of j such that you have this, and then you'd go through the proof and demonstrate this convincingly using all of the methods that we have developed to get upper bounds and lower bounds. So why this is important is because what you're doing is you're performing, or with applications, right? You're performing essentially advanced nonlinear functional analysis um, by just replacing the need to learn Picard's existence theorem later in a separate, real analysis course. You just learn it here. All right? So it makes a lot of sense. And really, okay, so let's take a step back. The differential equation. Okay, yeah, because we're going to move on to nonlinear analysis, but this is basically the end of linear thinking. So, and it kind of culminates in the realm of systems of ordinary differential equations, because what we do is we have solution spaces, right? And normally you would just like want to memorize specific solution forms of the solution spaces, but if you're thinking in terms of a more of an apostolian type of view of uh, linear analysis, vector spaces and dimensionality theorems come out, and we were talked about very early in calculus. Next one is existence and uniqueness. So usually you want to think about like omitting or stating things about uniqueness and existing without any proof. But from utilizing the first volume in obtaining specific bounds, and then using the metric spaces and fixed point theorem that gets talked about as well in this text, that kind of upgrades your, I guess, normally what you would expect to be an introductory type of calculus thing. Also, systems of equations. Normally people use elimination methods to solve them, but you get, a very basic calculus problem is just matrix exponentials and basic operator algebras that are used to compute things and motivate them properly. And then you have particular solutions, undetermined coefficients. Usually you have some undetermined coefficients, and then you solve for them. But he shows the annihilator method and operating factorization types of things. So that's very important. Okay, so keep in mind as we move on from linear analysis to nonlinear analysis, this is where the fun begins, to quote Anakin Skywalker. The derivative of a scalar or a vector field is not, you're not going to define it as like some, collection of some partial derivatives, but you're going to try to, as a linear transformation or the total derivative, you're going to try to best approximate the function locally. So you'll get, the chain rule for scalar and vector fields will kind of come out of this. But, first you introduce, open balls of sets, interior points, motivates a little bit of preliminary notions in topology. And total derivative, whatever is proven as composition. So here's a quote that I thought was interesting. Sufficient condition. A sufficient condition for equality of mixed partial derivatives. So you take a potential function, or you take just a function, and where are the mixed partial derivatives? Let's find them. They are sufficiently nonlinear. Okay, perfect. A sufficient condition for mixed partial derivatives, sufficiently nonlinear scalar field such that the partial derivatives exist on an open set. And you can think about just basically rigorously deducing the symmetry of the Hessian early on. And you'll get a nice linear algebraic formulation of the derivative by accomplishing this way of thinking about it. And you will treat in differential geometry this formulation of the derivative is exactly how it's treated in differential geometry, I would say, and the calculus of manifolds. So that is super important to get right from the get-go. Now we can move on to the applications of differential calculus. Okay. What this does is it says, well, we have extrema of functions in several variables, correct? And we have ways of thinking about them from the previous book and the previous chapter as well. We haven't really thought about extrema of functions yet, but we can think about the topological properties of the Euclidean space that was developed in the linear analysis, and we can utilize that heavily here. So, if a scalar, let's say, let's see, is a scalar field continuous? Come on. Yeah, that's being weird. But anyways, so if f is a scalar field of continuous at each point in closed interval, we can say it's bounded. This chapter is pretty computational. We'll just talk about Lagrange multipliers, extreme value theorem, in multiple dimensions that requires an understanding of compactness for cementing different ideas in topology. Now let's move on to the interesting stuff. So if we have line integrals are very interesting because he discusses work, potential functions, and the fundamental theorem for line integrals, which is essentially just the physics. It's just the background in the mathematics that you need for physics, and that's basically all this is. You can condition a vector field to be a gradient of some open convex set with, we can say, continuously differentiable. Yeah. Necessary conditions for a field to be gradient. So this is, he really develops this nicely, which is that if you have a vector field on an open convex set in S, then f is a gradient on S if and only if we have this condition satisfied. So this explores path independence very nicely and conservative fields to then rigorously establish what de Rham cohomology is all about. The concept of closed differential forms. And so, a nice background in this will then, and probably some differential geometry, would then give you then the tools to approach the language of differential forms and how they algebraic topology kind of naturally allows us to compute cohomology of differential forms. So, anyways, that's just stuff to get excited about. Um, Multiple integrals. So, integrating over integrating over several variables or over some domain with several variables. Um, how you can think about this is the definition of a bounded function over a rectangle. You can think about this as just the, let's see, it's the supremum. Where is it? It's rectangles. Or they partition it, and then how do they choose to find it? I remember seeing it nicely. Yeah, here we go. Perfect. So it's defined as essentially the supremum, or the supremum of S. It's called the lower integral of f, denoted by um, some lower integral here. And what happens is that the chapter is going to cover, evaluation by repeated integration, and you'll get this nice, like, rigorous analog to Fubini's theorem, like in measure theory. It just motivates that very nicely, so that next time you take a real analysis class or measure theory, if you want to further go into measure theory, like, I don't know why you would want to do that, but you can do that if you want. You can go ahead and do that. And then with the Jordan regions, Green's theorem, you get a change of variables formula for the Jacobian. And because the integral is defined using the suprema of step functions over n-dimensional intervals, you can just implicitly you're just basically doing Lebesgue measure theory by the time that you get out of this chapter. Okay? Then next, you'll do surface integrals. Surface integrals, or integrating over surfaces, usually you need some way to parameterize them. That's like the first thing that comes about. So if you have surface integrals over apostolian types of geometric concepts, you could say the solid angle, for example. Let's go to solid angle. I think the solid angle is probably the best way to start off with parametrizing, because it's the analog of the of it's the analog of the angular velocity, or sorry, the angular velocity of the angular dimension, but it's like you have like cones basically coming out. So it's a vertex subtended by S. Um, so it's the ratio of like the oh yeah, it just talks about it right here. Um, and by framing these theorems analytically, you'll be able to understand generalized Stokes theorems on differential manifolds, and integrate geometry into calculus. Um, and yeah, the last thing we'll talk about is elementary set theory and elementary. So it's set functions and elementary probability. But part three. So you have just traditional approaches to probability, whatever. There's different ways to motivate it. Um, you usually want to Usually probability is motivated combinatorically, but you are bypassing the entirety to produce probability via measure theory, which states that I think it's very gamblers dispute. This is the story that they choose to tell here. So, dispute in 1654 led to the creation of a mathematical theory of probability by two famous French mathematicians, Pascal and Fermat. And to formalize this, basically he's introducing the calculus of sets and Boolean algebras, and you can define a probability measure formally. Let's go. Come on. Yeah, so a finitely additive measure, or a probability measure, if you will, that's really how to think about it, is if you basically how to really think about probability is defining over um, things that are you measure these particular sets, right? You have the measurable sets from Apostles chapter 1, right, or from Apostles volume 1. Sorry, I'm just thinking about this. Like, what's the best way to intuitively do this? Because I mean, like, yeah, this does like a non-negative set function a to r that is finitely additive, adding a finitely additive measure or simply a measure, right? But I feel like that's a little bit. This is my own take with it. Like, um, really, what the defining key feature of a measure um, is really the Boolean algebra of sets. And when you are learning abstract measure theory, that's kind of what you want to think about. Like, so random variables, for example, defined as measurable functions out mapping outcomes to real numbers or whatever, right? That's kind of the way that you want to head towards. But like you have to bridge the gap between probability and real analysis yourself because um there's kind of a weird axiomatic type or the Kolmogorov axioms of probability, which I think will get talked about later. But they all get they're all fundamental, or they all come from something very fundamental, which has to do with measure and measurable sets, which then gives us measurable set functions. Okay, and it's your job to kind of fill in the gaps between what those things are, what they refer to, and how to make them rigorously motivated in that sense. So, um, yeah. Anyways, probably calculus of probabilities. Let's do. All right. So coming out of the elementary set functions, uh, we then now have the calculus of probabilities themselves. Probabilities themselves. What is probability, right? That's what we're going to try to answer. So continuous distributions, expectation, variance, all these things. All you need to know is, from our ideas of measurable, Borel sigma algebras, just how to generalize. Okay, sigma algebra is just how you generalize Kolmogorov axioms. Um, so we're approaching it from, again, this very pure mathematical standpoint, but you need continuous distributions, expectations, and variance, from whatever generating functions that you have, or you basically just need to treat them as integrals themselves. Um, and this is very nice. It's a very nice introduction to the subject. But and you can use calculus to study both one-dimensional and two-dimensional random variables, and that gets covered here eventually. It is kind of a longer chapter. Yeah. So you start off with the mass function. Um, all of these different ways of uh, building upon this density function, um, what probability really is. Now, that's a subject of debate in physics. um, Probability is really, I see it as just kind of defining some Hermitian structure on a configuration manifold, but that's just how I see it. um, People might have different opinions about what probability really is philosophically, but I don't really want to distract too much with this. It's very important to master the pure mathematical proofs that lead to measure theoretic probability. I'm trying to find, Cauchy distribution. It's also called Lorentzian distribution. for the reasons that detector physicists like to, or detector physics, gives us smeared infinite variance types of um, energy deposits on our detectors. So whatever. What else? How do we think about this? Um, the central limit theorem. Yeah, the central limit theorem. Uh, let's just go to that. That's much easier to think about. Central limit. The central limit theorem of the calculus of probabilities. Formalizing this. Um, basically, you have this nice proof here of like how if you had a bunch of random numbers, it just gives you a, and if they're independently and identically distributed, you get Gaussian type of distribution, taking the limit as n goes to infinity, whatever. Okay, so that's like how to that would be the central limit theorem, and then you'd also have Chebyshev's inequality, Chebyshev's in the discrete case. So this is how we find bounds, um, and the laws of large number types of limits. Um, so the integration of measure theoretic probability directly into a calculus textbook, is like an introductory calculus textbook is kind of, I would say this is a revolutionary type of achievement here, and he even does some citations as well towards the end. So this is definitely probably something that Apostle was very proud of creating. So go ahead and read through it and see what you can connect with what the planet Uranus was discovered in 1978. That's cool. Um, anyways, numerical analysis. This is the last one. And the history of numerical analysis goes back to ancient times. That's a quote that I have here. I don't feel like looking it up. You can. That sounds like apostle. But yeah, he goes through. I really really like this chapter, by the way. What a really cool read. You should go ahead and do that by yourself, and enjoy it. Um, yeah. So the ideas are going to be unified by notation and the terminology of linear algebra. Um, in numerical analysis. So you'll think about Simpson's rule. Let's just go ahead and try to find it. Simpson's rule, which is like trapezoidal approximation of areas. It's like quadrature. Where is it? I've played around with Simpson's rule plenty of times, trying to find some results and upper bounds on fractional calculus type stuff. So it gets used, I promise. If you have the dirty computational techniques, you'll be able to prove some new results and stuff like very easily. But yeah, Simpson's rule. Um, and numerical analysis isn't really that high skill of a subject either. It sounds kind of hard. It looks interesting, but like a lot of the times, you just have to kind of go through these exercises and see like, oh, there's Simpson's rule or whatever for polynomials. Um, so yeah, I mean, Euler's summation formula, Stirling's formula, those things are also in here. Error bounds on the, oh, let's do the Taylor remainder theorem. Come on. Getting error bounds on your Taylor remainders is pretty important as well. Oh, that was in volume 1. Yeah, so we already covered that. That's right. But yeah, I mean, just numerical methods aren't like pulled out of. They're not just generated out of thin air. You know, we kind of have to go through and do them with our brains first. And like then AI can kind of inference whatever from the method of numerical approximation that you're using, and diagnose how well it converges or how accurate it is or whatever. But you basically should be writing out. I mean, numerical analysis is a field of analysis, right? So it's pretty important to get right. So, anyways, I think I'm kind of rambling now, so let's just kind of end it. I just want to end it, guys. All right. Yeah. So volume one, volume two, right? You basically come out of both of these volumes as mathematically mature. I would say instead of just like blindly like a monkey, just like computing calculus problems like a like a monkey basically, like just grinding a bunch of calculus problems and trying to get like computing and computing and computing. This is going to get you to do everything. So it'll get you to do pure mathematics. You'll have computational ability. You'll have physical reasoning from this book, and you'll have historical accuracy as well. You defining derivatives of fields as these linear operators. Uh, Probability and the theory of finite additive functions. Continuous mathematics. So, like, if you go through this exhaustive two-volume sequence and you grind it effectively, that's going to replace the necessity for any introductory course in real analysis or measure theory, hands down. And the traditional real analysis course will it exists to primarily, I guess, fix the pedagogical errors of calculus. That's really all it is. It's just kind of a remedial type of calculus class. Whereas this is like the real stuff. It's not like the ghetto calculus, right? It's like this is the real shit. So you have the treatment of integration, anti-differentiation. Apostol never makes these errors. His students are forced into suprema, infina, uniform convergence, topological compactness from the very beginning. So, and also the Graham-Schmidt process, contraction mapping. I mean, I'm trying to remember what else like got mentioned. I'm like looking at my notes like from everything that I came across. Um, so yeah, you're gonna make sure that you're not gonna struggle with linear algebra and calculus as like these isolated types of disciplines. You will master these two volumes with just kind of a nice understanding of complete metric spaces, uniform convergence, operator theory, Lebesgue style bounding, guys. Like, very cool. So yeah, you'll be going through like a deductive exposition, also of mathematical analysis, and you're going to fulfill a lot of promises to convey this precise spirit of modern pure mathematics and fully prepare for the rigors of graduate level study. And notice I said graduate level. Doesn't mean you have to be a graduate student to pick up graduate level books, okay? Some people just think, and some people just want to read good books, and good books are graduate level. So a lot of them are. So this is a good, it's good philosophy. It's a good underlying philosophy for approaching the subject of calculus. Okay, that's all I have to say. Sorry for monologuing towards the end there. I was kind of reading from a script that I kind of wrote, so a script that I kind of wrote. If you get it, you get it. All right. Anyways, peace out, guys. Have a good one.